would be useful.
Coming through online, yeah.
Yeah. Okay. Great.
Yeah.
So yeah, a quick introduction to myself. Peter Matthias. I'm the rail lead at Tensor. I've been with the business around 8 years now. So it started off as the area civil engineer for the Northwest, moving on to the wider Northern Territory. And around 3 years ago, Tensor looked to set up a dedicated rail division, which partly due to the HS2 project work coming through, as well as our sort of ongoing engagement supplying various products into Network Rail schemes. So I'll give you a brief introduction to the team structure, and then we'll go into the applications where our products are used within the rail industry. So a relatively small team at present, myself as the lead, and we have technical and sales support sat behind us. So part of our early work with HS2, it became a prerequisite to provide our design services to go through the risks accreditation. So we have the Railway Industry Supply Qualification Scheme, both for the supply of our products as well as the related design services. So what you see today, we often support design consultants through to specification and giving them confidence in the solutions, but can also provide that in-house design service and get into contractual design as and when the project demands. The high compliance nature of generally rail and network rail demands that we have our products tested for a research and development which sits behind them. So as we'll go through, I'll touch on the relevant network rail product approvals that we have in place and some of the live ones that we have ongoing. So Tensor as a business, our GeoGrids are used in a wide range of applications. So as we're seeing the enabling works progress into main works on HS2, our products are being heavily utilised in anything from heavy duty haul roads through to crane lifting platforms, piling platforms, compounds, paved roads. Yeah, heavily applied across the scheme, with the general purpose of limiting the amount of excavation of generally softer subsoils and limiting the import of aggregate material, which not only due to the cost of importing these high quantities of quarried aggregates, but as well the carbon reduction. There's a lot of embodied carbon within the quarried extraction of virgin aggregates. So where we've been able to both demonstrate cost savings as well as the reduced carbon footprint, and obviously the time savings by the limited operations. Where I've come from this morning on the central section of HS2, we've currently got a temporary overbridge under construction. So steeping embankments leading to a temporary bridge abutment designed for sort of 5 to 10 years with a Bailey bridge plonked on top of it. So yeah, although maybe less aligned to the focus of PWI, just it gives a wider understanding of where our products are used across sort of general infrastructure leading into rail. Possibly of more relevance here will be our permanent work product areas. So we're getting involved with anything from permanent reinforced soil, load-bearing bridge abutments to steeping embankments, potentially repair of failing cuttings. Our products are sort of growing in uptake by the likes of Highways England, using these products not just within the initial trafficking to bring the materials in, but being factored as part of the in-service performance of a full pavement foundation. What we're going to focus on more today is obviously the products utilised within the trackbed stabilisation, and we break these down into two quite distinct applications within the sub-ballast and within the ballast layers. So we'll go into a bit of the research and development behind these products and look to see proven applications and some of the benefits that can be brought by them. What worked well with the Carlisle meeting, rather than sort of have a structured session focusing on the trackbed, because there was also people in the room who were interested on the reinforced soil structures. I'm going to quickly go through 4 or 5 slides, giving you a bit of a taster for where our reinforced soil systems for slopes and wall structures are used within the rail industry. So the scheme, the Bermondsey Dive Under in London, just trying to think how many years this goes back, probably around 8 years or so ago, just as I was joining the business. This was a published ICE paper. The sort of the background of this specific project, where there was the sort of the conscious effort to limit the carbon footprint of the project by using the adjacent masonry viaduct, which had been demolished. So they were able to reuse this demolished aggregate fill material, graded to the appropriate level, and use within the build-up of the reinforced soil structure. So you can see within that we've got the core of the recycled aggregate material, and then a frost susceptible granular layer effectively covering that. So the concrete modular block facing relatively slender, and then the geogrid reinforcement providing that effective restraint and able to support the subsequent live surcharging of the rail loading. Another project, which again was developed into an ICE paper, was the work at Reading train station, which probably dates back about 6-7 years ago now. Again, similar principle of using our modular block walls, using geogrid reinforcement to provide the sort of lateral restraint, as well as sort of get the fill material to stand beyond its natural angle of repose. So we're getting that to stand up at near 90 degrees with our modular block wall systems, and have the confidence to support the rail loading with a design life of 120 years. A more recent project example, which I was involved with, bit of a unusual application for reinforced soil. Reinforced soil walls tend to come into their own when we're sort of above 4 or 5 meters height, becoming more favourable over sort of traditional mass gravity walls and sort of reinforced concrete type solutions. But in this scenario here, it was the flexibility of the construction, the installation methods, which proved critical for the contractor. So working alongside Network Rail and their design partner and contractor, we were able to come up with a solution for a redeveloped station platform. So the existing platform was demolished and the footprint extended to allow for accessible walkway, and using the modular block construction with a limited excavation, the existing rail line was allowed to carry on operational. So the rail line, although it was in quite a remote part of Lincolnshire, the trains were passing, I seem to recall, around every sort of 3-4 hours. So when it came to the time of the train passing through, down tools, site gang, stand off, and then they were able to come back and then start work effectively. So that modular type construction really aided the progress of the installation on this one. We've got our modular block walls, which are anything from sort of 86 to just below 90 degrees, where we've got a requirement to steepen it up to, say, 70 degrees, what we classed as a strengthened earthworks rather than a reinforced soil structure. We've got the option to introduce a vegetated soft landscaping finish. So this will come in the form of our green slope system, which is pre-bent steel mesh facing units with brace bars to maintain the face alignment, and effectively getting the soil to stand up at a lower angle. We can use potentially a wider range of fill materials. So quite commonly we'll be using well-graded granular material to have the sort of the most efficient geogrid arrangement, but where potentially there's a bit more of a driver to use Site 1 fill material, we can potentially use Site 1 cohesive material, stony cohesive material, or various forms of PFA, leaker fill, various combinations that we've used on historic schemes. If anyone's into the rugby, you probably just about to see the Murrayfield Stadium in the back of this one, where we used a modular block wall construction close to the stadium, where the space was particularly restricted, and away from the stadium towards the training pitches. Again, we used a softer vegetated facing in the form of green slope. This one was quite an interesting selection of fill material. They used a lightweight expanded clay aggregate with around 25% the unit weight of a traditional fill material, and by utilising that, they were able to limit the amount of ground improvement at the foundation level.
Was that a complete new embankment there, or was it not?
It was a complete new embankment along that section, yeah. We've looked at embankments, we've looked at walls actually supporting directly the rail loading, but more commonly what we're getting involved with is potentially cuttings which are sort of starting to fail, or there's starting to be sort of early warning signs in terms of potential slip failure. Quite common techniques are use of gabions, for instance, or sheet piles, and what should I say, more heavy type solutions. Whereas we have, in the right circumstance, been able to actually use our geogrids with the failed material reinstated to then provide that design life for 60, 120 years. Obviously, with geogrids, we're reliant on excavation and then sorting through the fill material and understanding if the failed material can actually be placed back in. The ideal application of reinforced soils in a fill scenario, so where we can easily place the geogrids within the compacted layers of fill material. With cuttings, it depends how high that crest slope is sort of chasing up and sort of what sits beyond that. But again, in the right sort of scenario, we can offer significant value. An example here, a scheme in Scotland a number of years ago, before my time in the business, they were able to excavate out the failed material, or the section which was identified as having signs of potential failure, and then incorporate the layers of geogrid, reinstate the fill material, and have the confidence that that would then be serviceable within the subsequent design life. That's just a very quick run through of our reinforced soil systems. We'll principally now be focusing on our products used within trackbed stabilisation. So as I mentioned early on, we consider the application at the base of the ballast and lower down in the sub-ballast as two quite distinct areas. So we'll look initially at our products, our large aperture geogrid products, which were developed for ballast stabilisation, which is primarily there to provide the lateral confinement and limit the sleeper settlement, as well as some associated benefits with limiting the ballast fouling rates. And then we'll move on to sub-ballast stabilisation, where we're looking more at providing that increased bearing capacity, quite commonly to achieve a target formation modulus for the ballast layer to be constructed upon. But we'll introduce in brief our sort of developed design capabilities using finite elements analysis to factor in the benefit of the geogrid within the sub-ballast layer on how that affects the in-service performance. Let me mouth. So ballast stabilisation, most commonly employed during maintenance. So it typically, where with renewals and maintenance, we're generally not going any further than the sort of 250, 300 mil ballast build-up, potentially ballast cleaning and then incorporating that directly back in. The incorporation of the geogrid can be done quite practically. I attended the rail conference up in Scotland a couple of months back, and understand now that during all renewals, a geocomposite product is now installed. The relative low cost and the benefits that I've been seeing through its in-service performance become somewhat of a no-brainer. So with our products, the invent of the initial geogrid dates back to the late 70s, and then through into the 80s or early applications in sort of direct trafficking of wheel load. So looking at roads, compounds, those type of applications. But quite quickly after the idea of where the geogrid may provide benefit within rail came to throw. So in 1986 was the first look into how geogrids may affect rail ballast and how they would react under cyclic loading to sort of mimic what would be transferred through a sleeper. The early understanding of it was that the incorporation of a geogrid over a soft subgrade gave a similar performance without a geogrid on a firmer subgrade. So very sort of low level laboratory scale testing started to come up with the premise that over softer subgrade conditions, there may be the option to sort of limit the amount of ground improvement by incorporating the geogrid, or limiting the amount of excavate, replace, and subsequent build-up of ballast. And that led on to further work with British Rail. So they understood the general concept of it, and they looked to mimic that at a much larger scale. So they had a rolling stock rig which ran up to 2 million, effectively 2 million gross tons. So going backwards, forwards over multiple test section build-ups. So we had the control section over a softer subgrade, geogrid incorporated over a softer subgrade, and then a third section over a firmer subgrade. There was clear sort of early signs that the geogrid was serving some sort of purpose, and the conclusion was that the incorporation of the geogrid over a softer subgrade again gave similar performance to that over a firmer subgrade. That started the development of the use of geogrids into UK rail projects, and that led on to the major research project with the University of Nottingham, which was came under the Mercer Award grant. This was working alongside Network Rail, Scott Wilson as it was at the time, and the contractor partner. We're just going to dig in to some of the research and development and the full-scale site trial that went into that, to give you an idea of how geogrids were developed specifically for this purpose. So the Mercer Senior Grant, sort of coincidentally, Mercer, Dr. Brian Mercer is the original owner of Netlon, which then became Tensor. So a very clever person who came from a textiles background and actually invented the geogrid manufacturing technology. I'm trying to recall the year he passed away, but yeah, he's got an ongoing grant which goes into sort of innovative, pioneering type research projects. So the early work was to really understand, there's a range of different geogrids, which one would perform best, as well as a steel mesh product was incorporated within the small scale testing. That was combined with computational modelling, evaluating the full track bed, and from that there was then the adaptation of what was considered the optimised geogrid in the railway test facility to much higher cyclic level before being adopted on a live Network Rail test section. So let's move on to that. We look at the typical rail ballast gradients of the UK, typically sort of 30 to 55 mil. That was tested with various types of geogrid. Again, this was just using a sort of a bit of mimicked sort of rubber subgrade, various types of geogrids, and a steel mesh was evaluated. And from the testing, it could be seen that the size of the actual geogrid aperture had a massive effect on the performance. So the aperture was too small, it would resist the actual interlock confinement of the rail ballast particles. If it was too large, then it would slip straight through. So the optimized size was found to be around 65 mil, which is why you see within network rail, anything used within ballast stabilisation will have a 65 mil aperture size. So the correlation between that was that the gradient passing sort of 50% multiplied by 1.4 gave the optimum aperture size. Using this single geogrid specimen, this was then run through the railway test facility. So you can see the test setup there, preparing a sort of a relatively soft subgrade to sort of bring on the sort of the stress and the sort of the inducement of deformation more quickly, and then the placement of the geogrid with the ballast placed on top. So within the test facility, they had 3 load actuators. So through the 3 sleepers, this was transmitting a load of around 9.5 ton, which correlates to around a 25 ton axle load, which is sort of the maximum that we're typically designing for. Through the test, this was done with and without geogrid up to a million cycles. So from the result of this, we can see from the curve, the incorporation of the geogrid was extending the life before reaching the critical sleeper settlement limit of 6 mil by around a factor of 2.5 times. That gave the confidence to Network Rail to now put this into a live trial site. So this happened to be on the West Coast main line around the Wigan area, where there was going to be an increase in the speed of the line, and it was a section of track which was already encountering regular issues with frequent maintenance intervals. The site, as I mentioned, there is around the Wigan area, so not a million miles away from our manufacturing site in Blackburn, and so the relevant people from Tensor we were involved with ensuring the appropriate installation of the product and being involved with the subsequent follow-up on monitoring of the testing. So the investigation of deformation before and after installation of the geogrid reinforcement. I've got a nice little graph which will show you the levels of standard deviation which were being experienced before, and then subsequently what was achieved once the geogrid had been incorporated. So the track quality was reviewed frequently by a high-speed track recording coach. So I've got a lot of the work Tensor I've done previously based on sort of laboratory controlled conditions. The access to this high-speed track recording coach, taking numerous recordings, really sort of aided the development and the uptake of the product. So as you can see, over the course of 10 years or so, where they had the testing information, you can see the standard deviation, which was recorded over a 35-metre length, was encountering significant maintenance intervals. So yeah, you can see for yourself there a couple of years, and it was back in before subsequently reaching its limit.
That's for top.
What was that? Sorry.
That's the top vertical alignment. That stage, you know.
Yes. Yeah. So yeah, once the full track renewal was carried out, I believe the 0.6 mil standard deviation minimum was achieved at the start, which again, sort of quite uncommon to actually achieve that. And some of the associated benefits which we learn from experience with contractors is that actually incorporating the geogrid, because you've got that immediate interlock confinement rather than the ballast, which otherwise it's effectively loose, aids the actual placement of the track and has that sort of allowance for an amount of flexural stiffness, which can help achieve the sort of the required tolerances. From the graph there, we're actually, it's come up recently that we're trying to get hold of the extended curve from this, but over a duration of over 2 years after that, there was no requirement for any intervention, and this happened to be, so there was, what was it? There was, I think there was 8 different test sections which were reviewed. 2 of them which had the geogrid, which happened to be over the softest subgrade conditions. So again, over the softest subgrade, the geogrid was providing similar performance to the firmer subgrade conditions. Out of that multi-stage research project, we were able to demonstrate that the greatest impact on soft subgrades due to limiting the ballast settlement, and this was then incorporated to the Network Rail design specification, which has sort of been adapted into what we know now as the 4239 standard. As you can see there, an extract from the existing 4239 standard. Table 4 now gives you the option to design with and without a geogrid reinforcement for renewals. So again, the premise of that is that we're effectively designing for a lower overall stiffness, but that is balanced by the increased performance, which has been brought about by the stabilising effect of the geogrid. If we look at the related design curves to that, we can see designing for a 60 kilonewton sleeper end stiffness compared to that of a 30 kilonewton sleeper end stiffness can therefore limit the total granular layer thickness and the limiting the amount of excavation that goes together with that. So that is a major application for us with Network Rail, and we're seeing a sort of a steady increase in the application of the product. Back to the research timeline, we then moved on from our biaxial geogrid, so a square aperture, into triax, so a hexagonal geometry product, and we run that through additional testing, initially through the Czech Technical University, again demonstrating the performance improvement from our square apertures to our hexagonal geogrids, and some more recent work with the Penn State University across in the US. Quite a bit of a groundbreaking sort of piece of work to really understand the stabilising function of the geogrid. So these were 3D printed ballast particles with accelerometers incorporated directly to them. So similar to what you've probably got in your pocket with your smartphones, they can pick up on very sort of minute movements, rotations, and yeah, I believe each one of them was costing around £2,000 for a 3D printed ballast particle. So we'll have a quick look into how they actually looked during the test setup. So yeah, we were able to have the direct rail with the loading actuator being transmitted through into the sleepers over a thickness of ballast material, and then the 3D printed ballast particles incorporated at different depths away from the geogrid. So they weren't placed directly on the geogrid, they were placed at around 100 mil depth above them. So if we look onto this video now, we can see on the left-hand side, without the geogrid, the ballast particle more freely able to move and rotate, rather on the right-hand side, where we've got the incorporation of the geogrid, we've got minimal movement of the ballast particle due to the stabilising effect from the geogrid on the unbound aggregate. If we look at these sort of outputs here, we can see unstabilized is quite a high amount of particle movement as well as particle rotation, whereas where we've got the incorporation of the geogrid to provide this stabilizing effect, we've got a much reduced level. So this sort of leads on to sort of ongoing work which we've got going on at the moment, which is not looking purely at the sleeper settlement, which is obviously always going to be important, but potentially trying to look at quantifying what the ballast fouling reduction can be and linking that to the ballast fouling index. So that's very much live work which is going on at the moment, but hopefully that just gives you a bit of an understanding for things that we're even learning from what we did 20 years ago and still sort of testing the boundaries of what these products can do. So from the research demonstrated that the TX190L geogrid, large aperture Tri-X product, which has the Network Rail product approval, can extend the maintenance cycle by reducing the rate of ballast settlement and importantly now the degradation as well. This was presented as a business case to Network Rail, again, just before my time with the business, but it was trying to sort of highlight the particularly sensitive sections such as at switches and crossings, which when these are renewed, obviously there's a high impact, obviously the multiple lines crossing, and try to show a demonstration, partly looking to quantify what the incorporation of the geogrid will save over the lifetime rather than sort of upfront. So by incorporating that, we're expecting a limited amount of tamping visits, which if you run that through a period of 32 years, you can see roughly halving the number of tamping visits and extending the life of that ballast. So now within the 4239 standard, you will see within section 5.9, every renewal of switches and crossing should now incorporate a geogrid. Interesting section just on the use of these products linked to limiting the associated with decarbonisation of rail infrastructure. This was a slide I took from a PWI sustainability conference back in, I think, March of last year, where running the RSSB carbon tool, you could see the embodied carbon for renewal of a kilometre track for ballast, which I've sort of marked in a red box there, was around 26,000 kilograms CO2 equivalent per kilometre. There was a bit of a rounding error, which by the time it had come to October, we had another PWI event. There were some issues with the original tool, and you can now see with a kilometre renewal, the embodied carbon for the renewal of that ballast is now over 1.4 million kilograms. So a massive part of the actual embodied carbon within a track renewal. So if we're looking to either extend the life of the ballast material or limiting the sort of the settlement and the requirement for maintenance intervals, then the product can be associated with working towards meeting these targets linked to decarbonisation sustainability. So these the current products which we have Network Rail approval for, used directly in this application. So both the geogrid as a standalone product, and more recently we've gained Network Rail approval for our TX190L GM product. So where separation functions are also required, it's effectively laminated to the back of the product. So it's a single rollout process on site, and we have environmental product declaration for all our products. So if these do need to be fed into a carbon tool, that would be the standard source of input information. Moving on to subballast. So further down in the track construction, so this would be a full structural replacement or potentially new construction where we've got the scope to sort of deal with the problematic ground at source. We're generally looking to provide that required target formation modulus to support that ballast layer. Much of our early work across Europe was based on the EV2 static formation modulus, which is now sort of crept across to the network rail 2102 standard, which we'll touch on. So you can see a very sort of simple build up to the top left of a scheme in Germany, where we're reducing in that scenario there a sub-ballast thickness of around 1 metre down to around 700 mil. So that is generally sort of the approach that we're looking at for sub-ballast build-up. But again, we're pushing the boundaries in what we're doing in terms of modelling this through finite element analysis to understand how this works in service as well. We'll quickly have a look at some of the work at the Czech Technical University using the Triax geogrids. So this was a full-scale testing, and we used this Czech Technical University quite frequently, various new projects and so on coming through. And this was done to 250,000 cycles of a 40 kilonewton load, and rather than incorporating the geogrid below the ballast, this was incorporated below a relatively slender 150 mil sub-ballast build-up, with settlement pins included both at the underside of the sub-ballast and of the sleeper and the ballast layer itself. So preparing the subgrade, so like brick clay, broken down into a clay subgrade, and then the Triax geogrid being a standard aperture size to interlock with a more well-graded granular fill material, and you can see the settlement pins being incorporated. We did both a static plate load test with EV2 because we wanted to correlate the results against what is more commonly used with a dynamic plate load test. So this is generally what's happening on site, because it's a very simple test to do the dynamic plate load, although an EV2 will give sort of more meaningful results. So with the load actuator setup, you can see there, ran through the testing, and this was sort of for internal sort of confidence, really, to ensure that the application of triaxial geogrid compared to the superseded biaxial geogrid gave a performance enhancement, which you can see there by the reduction in the sleeper settlements. Interesting results as well on its impact on the resulting modulus of the material as well. So we run tests as the build-up was going up, and then once it finished the testing, also testing the resulting modulus as well. So I'm part of the track stiffness working group, which this is sort of quite a hot topic at the moment in terms of having meaningful targets and what should be tested for at construction as sort of quality control on what would be expected in service. So from the 2102 standards, correlating that from the 4239 for the minimum dynamic sleeper support stiffness, this is correlated to a dynamic modulus, as you can see to the right hand side. With the table 3 from 2102, this then converts it to an EV2 target modulus, which tends to have extensive experience from. A lot of it linked to the design of haul roads and crane hard standings, where in Germany that is generally the test approach. So where we'll have German sort of wind turbines being imported into the UK, the delivery of those will be linked to the road or the hard standing having a target EV2. So we've got quite an extensive background of designing to that, which again the standard is following the German DIN standard in the network rail standard. Looking back to the design curves, which we've seen earlier, so from a target of 60 kilonewton sleeper end stiffness, if we looked at an undrained subgrade modulus of around 10, which is around a CU of 40 kPa, we can see that's roughly that green line is around 750 mil, which is what we've got on the left-hand side of the slide here. Where we're designing for just the sub-ballast build-up, we can design for that 60 MPa target formation, reducing the thickness down to roughly around 350 millimeters. So in that particular scenario, again, we're reducing the thickness of granular layer by around 200 mil, and obviously the associated excavation depth as well. This is used quite commonly across Europe, in parts of Europe. They don't tend to like using geogrid directly behind below the ballast, linked to sort of historical sort of interpretations and linked to their particular maintenance equipment as well. So yeah, the geogrids tend to find themselves lower down in the subballast buildup. That is what Tensar have done till probably 2018-19, until we tried to move on from just designing for a target formation modulus, and similar to what we do in road pavement applications, we try to sort of find the benefit of the geogrid in service performance. So if we look at this extract from the Network Rail earthwork strategy, see the key variables affecting track deformation are axle load, and to a lesser degree the number of load applications. So when we're designing for a target formation modulus, we don't even consider the axle load. So that's a bit of a thought opener to think, right, okay, we're designing for a generic formation modulus. Are we actually designing for what's going to be trafficking it over it? Effectively, we're doing exactly the same as what we would be on a road or a crane lifting platform. So some of our sort of technical gurus within the business sought out to look at established rail design methods, more linked to in-service performance. The Lee Selig method, seen as one of the most sort of established, accepted methods sort of across the globe, used extensively in the US and I believe in sort of parts of Asia. There are limitations with it being elastic layer analysis, and that's what we sought to look to adapt to a more simplistic approach, which could be shown to have the benefit of the geogrid included. So the progressive shear failure mode of failure was principally what we were looking to control. So limiting that to a suitable limit. So when we're at one axle pass, the N and the B effectively become one. So the strain at the first loading rate is A, which I'm not going to go into detail on this, but you can see there's a number of variables linked to a very sensitive input of soil types, stress state, and soil state. It's accepted within that design methodology that it's very subjective and linked on the sort of competency on the person inputting that information. So we looked at a different approach using finite elements analysis to work out that tricky A parameter, and then the B parameter being a relatively straightforward geotechnical sort of handbook type characteristic. As well as the progressive shear strain, this could be adapted to calculate the permanent strain following the appropriate number of axle passes from the sort of annual gross million tonnage. The work to sort of model and show the performance of the geogrid was not to look at the product in isolation. So the geogrid is not a high tensile product which is used within a sort of a basal reinforcement for an embankment or a load transfer platform. It's principally used to stabilise the soil material. So Tensar own sort of two of the largest triaxial compression tests in the world. I think there's around 4 or 5 of these. Tensar own 2 of them. So these are 500 mil diameter triaxial compression tests. So geogrids incorporated with various fill types, various geogrids, and we're able to understand what the effective shear strength of this stabilised aggregate is. So as we can see there, this geogrid has an influence effect of around sort of 350 to 400 mil, and through the testing on this, we can quantify that and incorporated it as a plugin to various FEA type programs. This then allows us on specific projects, if we're there's particularly complex ground conditions, for instance. So we've got a competent crust overlying quite a soft subgrade. We can model various subgrade types, sleeper types, rail loadings. There's a lot of flexibility to give a deeper understanding, but as well incorporate that benefit of the tensile stabilized soil. This was peer reviewed actually by the original author of the Lee Selig method, and that was presented at the AREMA conference in the US early this year. And a copy of that I can make available if anyone's interested. But yeah, believe me, it'll take a good while. Yeah, quite heavy reading, but yeah, gives an understanding to the design methodology, so where we're going with this. On every project, we're not expecting to go into that level of complexity, because it takes highly specialist engineers within our business and sort of the associated cost with it. So we've been able to adapt that into spreadsheets, and sort of, as you'll see now, in the form of Tensor Plus, you can log in directly to our website and go onto our different design modules if you want to design a haul road, a working platform, and now looking at rail sub-ballast design. So you can input all the relevant parameters that you might expect, anything from the wheel load to the diameter, the rail type, and get an understanding of what those build-ups are going to result in terms of the progressive subgrade shear strain and permanent deformation. The idea is then that we can design based on the project requirements. So if we're looking at the sort of the conventional control section on the left-hand side, we can look to either save upfront costs by reducing the thickness as far as possible, or actually maintain the existing thickness and incorporate the GeoGrid and take the benefit over a full life cycle. And again, incorporating the GeoGrid below the ballast as well will provide that limit on maintenance intervals. The first major UK application of the design method was in Belfast. So that was constructed earlier this year, with the design process going through probably most of last year. The interesting one here was that the design, typically what we do for an EV2 target formation, was rejected by the client because they were concerned with the Belfast Sleech subgrade materials, a very soft organic-y type clay material. And yeah, there was concern that over time, although it was a relatively competent crust, it was going to result in deformation and yeah, insert of maintenance. Within the specification was a zero maintenance for 5 years. So obviously the contractor was quite wary on that. So working together with the two design partners, we work collaboratively with them, sort of guiding them through the design methodology and using our in-house FEA specialist, and working together with their FEA engineers to model the actual track construction, and carry out various models for the different conditions along the section of track, because the subgrade vary quite significantly below it. The resulting track bed construction, as you can see there, with the standard aperture triax GeoGrid TXR product incorporated within Type 1 sub-base material, and then the TX190L GM product incorporated below the ballast to again just limit any mitigate the differential settlement and ensure there wasn't going to be the requirement for ongoing maintenance. So that's the project under construction. So that was me taking that back in, I think it was about February time, and yeah, I don't think the sort of the upper track has yet been placed, but yeah, we'll be keeping a close eye on that one. Again, Network Rail certificate of acceptance for the TXR GeoGrid and the environmental product declaration sheet to go with that. Just finishing up now, so we've covered sort of ballast and sub-ballast applications. I'll just give an overall now on where yeah, so the general principles I think we've seen in terms of limiting stone thickness, limiting excavation, but also used in yeah, I should say more niche type applications. So I think we've seen with the potential to minimise ballast degradation, increased trackbed stiffness on top of the sub-ballast layer. So a high-speed line in Russia, where again testing for the EV2 target formation modulus. The case studies are available directly from the Tensar website. Reducing ballast settlement. This was one of our largest schemes over the last sort of 4 or 5 years. The Aberdeen to Inverurie line, where large quantities of TX190L geogrid were incorporated within the major renewal. A very interesting area, and I know it's catching quite a lot of attention with the track stiffness working group, and probably a headache for a lot of rail track designers is both looking at limiting the trackbed variability. So that's a sort of a more general scenario, just slightly varying subgrade soils. But a more extreme version is where we're going potentially from slab track onto ballasted track, or approach to over bridges, where our geogrids have been used sort of extensively more as a detail without any sort of major technical backup behind it. And that's an area again using the FEA capabilities now, where we're looking at that. And there's a couple of projects which we're putting a bit more effort than we would usually, because unfortunately they're relatively small area applications, but again there's multiple ones of them. So it's an interesting area which we're certainly looking into and trying to develop on what we're doing already. I didn't even think about this actually, but yeah, the case study for this one's Crewe Green Link Road, which I can only assume is fairly close to here.
Yeah, just over there.
Yeah, so you can see the Tri-X geogrid being incorporated below the ballast there, transitioning from the I assume that must have been the raised embankment over the
bridge line, isn't it? KCS1 right there, and then the road going under it. Yeah.
So again, case studies available. I didn't even think about this one, to be honest. It's just one of our standard case studies. But yeah, this is certainly an area which we're pushing on with now, because we're getting regular feedback that it's again relatively small areas, but big headaches, and we can be seen to be a solution provider. Then that's what we're looking to achieve. So that's me. Hopefully I've kept it roughly in time.
Fantastic.
And hopefully that was useful and relevant to you.
Yes, brilliant. Thanks for that, Peter. Is it worth going out onto the Teams call just to see whether any questions are coming? So if anyone in the room's got any questions for Peter, feel free to raise them now. Likewise, if anyone on the call has got any questions as well, feel free to put your hand up or post them in the chat. And I'm sure Peter will be happy to answer them.
Just got one, Peter. Going back, I don't know, 8-10 years now, I remember there was a bit of a fad with geogrid, where we were being instructed that it had to go not on the bottom of the ballast, but you had to lay a thin layer of ballast, then put your geogrid on, then put the rest of the ballast on. The theory was, I believe, that you got improved ballast interlock, which might contribute better towards the stiffness of the completed track there, but that seems to have fallen by the wayside now. Is there any sort of truth in that, or
interesting. I can show you a link. There was a summary done by Dr. Nick Tom from the University of Nottingham. So the research, the large scale research project that we did actually placed the geogrid at different positions. So 100 mil above the ballast and directly below the ballast, and there wasn't any performance difference. And then in terms of the practical installation, that's a large driver of it as well. That incorporating the grid directly below the ballast is going to be a much more practical operation, both for the initial installation as well for any sort of ongoing maintenance. So keeping that sort of the tamping head sort of within sort of the immediate influence of the geogrid but yeah, that's why we're generally looking to have it down at the base.
That image you had of Crew Green Link Road, was that composite sleepers then installed there? I don't know if you've got the image to hand there. It's just quite interesting because that location is actually within, I mean, unless one crew program that is within our footprint, within the Alsage resignaling limits. So yeah,
Let's have a quick look. It was on, yeah, it was on that slide, wasn't it? So this was my colleague. He worked for Tensar and then worked for Morgan Sindall. And I think it was during that project where he was at Morgan Sindall, he was able to obviously have sort of live experience of the products being used here. So I'm sure he's got a better understanding of the sort of the project build up than what I can share.
yeah, the point about the transition for underlying structures was one of many things in there that piqued my interest with my crew program out on, because we've got some really shallow subways at Crew Station as an example over quite a short length. We've got the independent line tunnels that come out under Crew North Junction, which are relatively shallow. We've got a few under bridges as well. So I think it's always something which is a bit of a concern to us about that transition, particularly when you're talking about, I mean, those subways are about 200 mil below sleeper bottom depth or something along those lines. Okay. West Coast Main Line, Cat 1A track, 80 mile an hour. It's we're kind of progressing through the back end of Form A at the moment, design, but always I think looking out for potential solutions to alleviate that in a cost-effective manner, particularly.
Certainly more attractive using geogrid, that approach than your traditional concrete transition road. Yes,
so that's quite often where we're sort of being considered as an alternative to that. So again, I can share some recent details from projects where, again, this was just where the geogrid was incorporated through the ballast layer and just had that level of consistency. But what you'll often see on the exit from the overbridge is that you'll start off with quite a significant thickness of sub-ballast with the layers of geogrid, potentially multiple layers of geogrid within the sub-ballast, and then it'll bench up until it sort of transitions onto the plain line track. And again, that needs to be considered as sort of the global track components, where potentially use of undersleeper pads and other other products within the track can give that more controlled level of stiffness from your stiffer part to your plain line.
Have the biaxial geogrids fallen by the wayside for railways now? Is it all triaxial generally?
From Tensar's perspective, it is. So we do have legacy biaxial geogrids available, but they're generally manufactured to order rather than our triaxial geogrids are available from various distributors. So a contractor needs 5 rolls, they'll just go into the local Keyline or Burdens branch and bring them to site. So yeah, we tend to see the general application of it being that. Although on some projects where that historical biaxial spec is still there and you struggle to shift it, then yeah, there's still the option of that. But yeah, the supply of that can be say a little up and down.
Something worth bearing in mind, that, because I think often have that as a bit of a legacy, don't we?
I think from memory now, a general note that gets copied from one drawing to another talks about biaxial.
I think it does, yeah. I was just thinking that.
Yeah, a bit of SSLA 30 biaxial geogrid, which again we often see it, and again we often put forward the alternate product which has the superior performance. But yeah, both products are technically available. Which one is sort of, yeah, unless we've got a forward view of it and it's a large enough quantity, then it's not readily available. What we're starting to find now as well with the legacy biaxial products, we haven't gone to the effort of carrying out the environmental product declaration with them. So we're rail projects, and certainly with HS2 is becoming sort of prerequisite to have an EPD for these products, which the triaxial product range has. whereas the biaxial products, it's a very costly exercise to have them done. So that monitors every part of the manufacturing process, from the import of the polymer chip to our Blackburn manufacturing site, to do multiple runs of it. And we have 100% green electricity, so all that sort of factored into the product, and sort of the subsequent use of it.
Brilliant. Did we have any more questions on the Teams chat, or anyone else in the room? I think we obviously attendance has suffered a little bit today because of I think rail strikes in the room, and because of being school holidays as well, half term. But Peter's kindly agreed for this to be recorded and shared on the PWI Knowledge Centre. So that'll mean that this becomes available on YouTube for anyone to view. So I'm definitely going to make sure, from kind of my personal perspective, to share this with all of my civils colleagues as well, because I think there's probably another talk there in itself based on some of the stuff I mentioned at the beginning, which would really interest a lot of people, particularly embankment stabilisation, kind of within a wider Network Rail context.
Yeah,
really pertinent point. And additionally as well, as I think we were touching on there, is something that I'll definitely be looking to share with our trackbed design colleagues, and particularly within Atkins. I don't know how much maybe involvement they necessarily have with things like the track stiffness working group, but
Hannah Carey is on it.
Hannah Carey, yeah. So
I know her, but I don't know how, if she's with your colleagues.
She is actually.
Okay.
So we'll make sure to share with her and her team for sure. And yeah, if anyone on the call, feel free to share it as well, because it's a really interesting presentation, and it's I think for me particularly, as someone who's gone to the railway within the last 10 years or so, seeing the development of the GeoGrid was quite interesting, kind of through obviously well before my time, and seeing how it's kind of come into being business as usual. Having always worked in track renewals, it's always just been there for me, and I've always just took it for granted. But it's definitely interesting to see the work that was done, pioneering work that was done previously, and also the pioneering work that's still being done as well. Particularly the research you referenced in Penn State was pretty fascinating, with those accelerometers in the 3D printed ballast, and I'm sat there thinking that that'd be really useful. I think in a lot of kind of monitoring applications elsewhere. I know it wouldn't necessarily be in the controlled environment the same way, but really fascinating research. I think as well, more generally, just looking at Tensar's products and the applications, not just within trackbed design, but also within the wider rail infrastructure. As an institute, the PWI, we've had a particular focus in the last few years on kind of making clear that we're an institute for rail infrastructure engineers. So obviously covering off civil engineers, people in trackbed design, etc. So it is really good when we have a presentation that kind of touches on multiple disciplines, if you will. And before the meeting, I was saying to Peter that even though I'm a track engineer, I often kind of, within our design specifications, we're quite broad with what we mandate, and we obviously take a bit of it for granted, ensuring that we're complying with our standards. But I think going forward now, I'm going to have particular more focus on what products we are actually using, because it's just fascinating to see the different range of things available from Tensar. So yeah, it's been great having you here today, Peter. Really appreciate that.
Thank you for the invitation.
We obviously look forward to sharing it as well with the wider community. And yeah, if everyone in the room and on the call is able to give Peter thanks in the normal way, that would be much appreciated. And I think just section announcements, as Les said previously, this is our last talk of the 2022-23 calendar. It's been a really good programme, and really appreciate all your support throughout the calendar year. We're going to be giving some news relatively shortly, hopefully in the next month or so, about some of our talks we've got lined up, which are recommencing from the first Thursday of September. We'll have to double check the date. I don't know off the top of my head. And we're also going to be looking to try and put out some feedback forms to the section over the summer, just to try and get a little bit more view from yourselves as to what talks may be of interest, and also what visits may be of interest to those of you. So yeah, just to say to everyone, thanks again to Peter. Have a great summer, everyone, and look forward to seeing you again in September. Brilliant. Cheers for that. Thank you.
Switch off. Yep.
Yeah, thanks, Pete.